In this video, we are going to evaluate this integral. We're going to do it in sort of a convoluted method by applying the Lebon's technique of differentiating integrals. The playlist for the videos is at the website digital-university.org. If you go there and click on free calculus videos and then scroll down to where it says differentiating integral functions, you see the first 3 videos were all developed or devoted towards developing the Lebon's rule for differentiating integrals. It's this general expression here. And this video, we're going to use this now to evaluate this integral. So if we look at this, we have e to the minus t, then we have another variable, e to the minus bt, on the second term here. So let's say that we'll call this integral, we'll just call it I. And it's going to be, if we were to evaluate it, we know it's going to be some function of b, because the t's, once we get an expression for it, are going to be replaced by 0 and infinity, leaving only b. Also notice that our limits are constants. They are not functions, which means that if we try to differentiate it, this term and this term are 0. When we develop the general form for the Lebon's integral, or for the Lebon's differentiation method of integrals, these were functions here. In our problem, they are constants, so this derivative is 0 and this derivative is 0. So if we take the derivative of I, of that integral, we'll just say di, take the derivative of that integral with respect to b, that would just be then moving the differentiation process inside of the integral. So we have the partial of b of e to the minus t minus e to the minus bt over t dt. And taking this partial derivative, that's going to be 0. So this will equal, we have 1 over t. That's 0. The partial of this with respect to b, that will be e to the minus bt. We have a minus sign here. And then this will be minus t that comes down here. dt. So this is just simply going to be equal to the integral from 0 to infinity of e to the minus bt dt. And this will equal, that's a very simple integral, minus 1 over b, e to the minus bt. T goes from 0 to infinity. So this equals minus 1 over b times, t is infinity, 1 over e to the infinity, that's 0, minus e to the 0 is 1. So this equals 1 over b. So all we did was have this integral with constant limits. We took the derivative of it with respect to b. And we could do that in the very first step, is to differentiate inside of the integral sign. That's what this first term is. But now, because these limits in our problem are constants instead of functions, these two terms are 0, so we only have this term to work with, and that we have right here, and then taking that partial derivative gave this expression. We integrate, we have this. So then what we have is the derivative of this integral with respect to b equals 1 over b. So we're just calling this I, so we're just treating it like it's a variable, and what we have is di db equals 1 over b. So multiply both sides of the equation by db, and we have di equals db over b. Again, just treating the I as a variable, we can integrate, and we have I equals the ln of b plus a constant. But what is this variable I, or what we've been treating as a variable? It's that integral. So let's write this down here in place of I, and we will have now we have an expression for what this integral is equal to. Now let's consider what happens when, say, b equals 1. So that will equal the ln of 1 plus c. Over here, b is 1. Oops, we forgot to put our dt in. When b is 1, this is 0. This is 0 on this side. The ln of 1, that's 0. So it means that our constant of integration c just equals 0. So what we have then, we'll write a little bit more neat in just a moment, or let's just go to the top of the page. Our original integral, what we called I, equals this. So we go back, this equals the natural log of b. So here we have a demonstration where we can use, where we differentiated an integral. Then once we had that equation, that is that di db equals 1 over b, we differentiated our integral with respect to b. We were then able to use this equation to solve for what the integral I is, and therefore we were able to solve this problem. So the thinking is a little bit convoluted, but hopefully now you start to appreciate that using the Bond's rule for differentiating integrals can be a very elegant method to evaluate integrals that otherwise might be impossible to do. We'll try to have some more demonstrations of this method in some future videos.